Gábhíle sa cúig ag pop ar a hainceist a hooked. An oil spill occurs offshore in an area of calm water with no currents. The oil is spilling at a rate of 4 by 10 to the power 6 centimeters cubed per minute. The oil floats on top of the water. Question A, Part 1. Complete the table below to show the total volume of oil on the water after each of the first 6 minutes of the oil spill. So after 1 minute, it's going to be 4 by 10 to the power 6. So that's included here in the units. So we're just including 4, 8, 12, 16, 20, and 24. So just to note, we're multiplying the volume per minute to find the overall volume over time. So the next thing we have to do is just plot these points in the graph. So after 1 minute we have 4, 2 minutes we have 8, and so on. So that's about as accurate as I think I'm going to get it without a ruler on the computer, but obviously using pencil being as accurate as possible with any graphs. On to part 3. We need to write an equation for the volume in terms of T, the volume of oil on the water after centimeters cubed, in centimeters cubed after T minutes. So even if we look at what we have, in order to find the volume after T minutes, we've multiplied the minutes by the volume. So therefore, our volume in terms of T is going to be equal to 4 multiplied by 10 to the power 6 by T. B. The spilled oil forms a circular oil slick 1 millimeter thick. Write an equation for the volume of the oil in the slick in centimeters cubed where the radius is or centimeters. So the volume that we're looking for is the volume of a cylinder. What we need to watch out for in this question is that we've got a lot of units to just keep an eye on. Here they've given us the height of the cylinder as 1 millimeter. So we want our answer to be in centimeters. So straight away really we should change this to centimeters just to avoid forgetting it at the end. So in terms of ore, we want a value for this. They told us that this is equal to 0.1 centimeters. So the volume is equal to pi ore squared h for a cylinder. Pi, the radius we don't have, we want it in terms of ore. And height we do have, shin 0.1. So just tidy up 0.1 pi ore squared for the volume. And this is centimeters cubed for the units. Part 2. For us to find the rate in centimeters per minute at which the radius of the oil slick is increasing when the radius is 50 meters. Again, before we were doing millimeters, we had to change that into centimeters, and now we're dealing with 50 meters. So again, the first thing, before I do anything else, I'm just going to make a note of that in centimeters. So we have 5,000 centimeters because they're asking us for the rate in centimeters per minute. So first of all, we just have to kind of translate what they're asking us to do. The rate of change of the radius. So this is d or dt, how the radius is changing over time, when the radius is equal to 5,000 centimeters. So d or dt, this is going to be equal to d or dv by dv dt. We know that we have to do this because we don't have an equation with radius with respect to time. We do have an equation with volume with respect to time in just the previous part. And in part 1, we do have a formula for v with respect to t. So we're just going to come back to these in a second. So this really is the key to the question. These are the two parts we need to find in order to find d or dt. So like I said, we have v in terms of ore. V is equal to 0.1 pi ore squared. If I differentiate v in terms of ore, I'm going to get 0.2 pi ore, and therefore I can find d or dv. So d or dv is just going to be 1 over 0.2 pi or. So I'm just going to make a note of that up here because I'll run out of space. So the next thing I need to find is dv dt. Again, we need to just refer back up to part A. So we know that we have v in terms of t. So v is equal to 4 multiplied by 10 to the power of 6 t. So I can find something for dv dt. When I differentiate in terms of t, I'm just going to get 4 multiplied by 10 to the power of 6. So going back to our d or dt, which is what we're looking for, we fill in d or dv, so that's 1 over 0.2 pi or, multiplied by 4 multiplied by 10 to the power of 6, and we simplify. So we're looking for d or dt when or is equal to 5,000. So we substitute or in. And using the calculator to do all of the work really, remembering to put in pi, we have 1273.3, and that's centimeters per minute for the units. So just to put it in context, that's the rate of change of the radius of the circle of oil as it's changing over time in minutes. C. Show that the area of water covered by the oil slick is increasing at a constant rate of 4 by 10 to the power of 7 centimeters squared per minute. So really what they're asking us to show is that the rate of change of the area over time is equal to 4 multiplied by 10 to the power of 7. So we're going to kind of approach this question the same way as we did the previous part. dA dt is equal to dA dor by dor dt. So you might think, okay, how do I know that it's dA dor? How do I know that it's not dA dv times dv dt or anything else? It's really about making that link between the things that you already have. So for example, the previous part, we just found dor dt, so we know that. And also, we know then that we have a formula relating area to the radius of a circle. So we have area is equal to pi or squared, so therefore we can always find dA dor. So that's just even a handy one to know for these types of questions. And it's the same kind of thing for the volume or any of those things related to area and volume of all the different shapes. We should always kind of have those in the back of our mind when we're dealing with questions like this. So dA dor is just going to be 2 pi or. And as I said from the previous part, dor dt we found was 4 multiplied by 10 to the power of 6 over 0.2 pi or. So all we have to do is substitute these two things in. So dA dt is going to be equal to 2 pi or multiplied by 4 by 10 to the power of 6 over 0.2 pi or. So when I simplify, pi and or are going to cancel. 2 divided by 0.2 is going to give me 10. So that's 10 multiplied by 4 by 10 to the power of 6, which is equal to 4 multiplied by 10 to the power of 7. And the last part, they say that the nearest land is 1 kilometer from the point at which the oil spill began. Find how long it will take for the oil slick to reach land. Give your answer to the nearest hour. So to break this down in its most simplest form, they're asking us about time. We know that time is equal to distance over speed. Okay, so it's not just as straightforward as that. What we're looking for is, instead of distance, the area that it's covering divided by the rate at which it's traveling, so the speed. So the rate of change of area over time. It's not strictly distance over speed, but there is a connection between those two things, just to make it a little bit more straightforward. So this area that it's traveling is not necessarily the direct distance in a way in terms of the circle. We are talking about the radius being equal to 1 kilometer. Because we've been dealing with everything else in centimeters, so the rate of change of the area and everything else in centimeters, we need to change 1 kilometer to centimeters, and it's 100,000 centimeters. So the area that it's traveling is pi r squared, and the rate at which it's traveling is dA dt, which is equal to 4 multiplied by 10 to the power of 7. So now I'm just simplifying. Instead of squaring 100,000 and writing that out, we're just going to write it as 10 to the power of 10. That's the shorter version. Over 4 multiplied by 10 to the power of 7. So we're going to be left with pi 10 cubed divided by 4, which is going to give us 785.3984, and that's minutes. So that's minutes again, because the rate that we're using is centimeters per minute. We're using centimeters, so our answer is minutes. They ask us to the nearest hour, so dividing this by 60, we're going to find 13 hours.